Okay, next is proposition 192. So let us recall that in the previous video we saw the cycle space of a graph, which is defined to be the subspace of the edge space spanned by all the cycles in a graph. And we have also seen another proposition which appeared before this one, which says that actually the cycle space is in fact also spanned by all the induced cycles in the graph, that is, smallest cycles are chordless cycles. Now this one says that it gives us three assertions, three statements about general edge sets in a graph, that is, E is the set of all edges in a graph and F is a set of edges, that means F is a subset of E. The first one says that F is an element in the cycle space, that means F is a vector in that space. The second one says that F is a disjoint union of cycles in G, or more precisely, F is a disjoint union of edge sets of cycles in G. That is, there are some finitely many cycles which are mutually disjoint in the sense that if you choose any two of such, from that list of cycles, any two cycles if you choose and consider the edges in the cycle, then there is no common edge. And so for each cycle you choose the set of its edges, you then get mutually disjoint sets of edges. F is the union of those sets. So the union is a disjoint union. And the third one says that all the vertex degrees of this graph are even. That means, being a set of edges, F will generate a subgraph of the original graph G, whose edges will be precisely the edges in F. So in that subgraph, all the vertices will have even degree. Now the claim here is that these three statements are equivalent to one another. That means if one of them is true, then so are the others. And the proof in the text goes like this: since cycles have even degrees and taking symmetric differences preserves this. That is, because cycles have vertices of even degree, and if you take the symmetric difference of the edge sets of two cycles, then this evenness is preserved, which you can see. There will be some cases depending on how those two cycles intersect each other, that is, whether there is a common edge or not. For example, let me show you. Say this is one cycle, a 5 cycle, and this is a 4 cycle. Okay. Now because there is no common edge, so if you consider the edge set of this cycle and the edge set of this cycle, they are disjoint sets, and their union is actually the sum of these two cycles in the cycle space, which will give us the set of all these edges. So here the degree of this common vertex is 4. 2 comes from this cycle, 2 contribution. The other 2 is contributed by this 4 cycle. A more complicated situation may be this. Okay, say this 6 cycle and this 5 cycle, there is one common edge. Now when you take the sum of these two cycles, then because the sum is actually what? It is actually the symmetric difference of the edge set of this 6 cycle and the edge set of this 5 cycle. So the common edge will be removed from that, because that's what symmetric difference does. And the rest of the edges will give us a set. That set is actually the result of that sum or symmetric difference. So that means, you see, originally in this graph, of course, the degree of this vertex is 3, but this is not the graph we are talking about. We are talking about the symmetric difference of these two things. So when we take symmetric difference, because this common edge is vanishing, so the degree ultimately becomes 2, and the vertices which are unaffected by this process, they of course retain their degree, original degree. If it is still more complicated than this, then it may be something like this also. So this is also a 5 cycle, and so you consider this. So 1, 2, 3, 4, 5, 6, 7. So this is the 7th cycle. Now when we take the symmetric difference of these two cycles or the sum of these two cycles, then these two common edges get deleted, and as a result we do not have to think about this vertex. Why? I mean, we do not have to think about this vertex in this subgraph. In this subgraph, this vertex will not be there, because this subgraph is being generated by edges, and this vertex is not incident with any of these edges, so it will not be there. So this subgraph looks like this. So that is why these vertices whose degrees are affected still have even degrees, and those that are unaffected will stay unaffected. Okay, so that is why, I mean, in general also this happens, that if you take the symmetric difference or sum of a number of cycles, no matter how they intersect one another, the evenness of the degree is preserved. And that is why, because this is preserved, the implication 1 implies 3. Follows by induction on the number of cycles used to generate F. Now if you think about the actual induction process, it goes like this. So we need to prove 1 implies 3. That means it's given that F is an element in our cycle space, and we need to prove that in this subgraph, for example here, in that one, or here, all the vertices are of even degree, and the induction is on the number of cycles needed to generate F. Now F, being an element in the cycle space, will be a linear combination of cycles, lambda 1 C1 like this, where the Ci's are cycles in the graph and these lambda i's of course are coming from our two element field consisting of a zero element and a unit element, a unity. And our induction is on n, the number of cycles involved in this linear combination. Now you can note one thing here, that each lambda I is either 0 or 1. When lambda I is 0, the corresponding cycle is actually not there in the linear combination. Whereas when it is 1, then it is just there. That's what, that is the role of lambda I. Because we want to apply induction on the number of cycles that are actually involved in such a linear combination. So without losing generality, we can just assume that all the lambdas are 1. And then we apply induction on n. So how does the induction process go? Because we need a starting point, a basis, so we need to look at the case n equal to 1. So when n is 1, then our f is just C1. This equation, this equality should not be taken literally. That is not true. On the right side, we have a graph which is a cycle, and to the left of the equality we have f, which is actually not a graph but a set of edges. So what this equality truly means is that f is the set of edges in C1. So that way we have to interpret. In fact, this equality also. Okay. Now when f is C1, what is this subgraph that f will induce in G? It is C1 itself, because we are taking the edges of C1, so those edges generate a cycle. So that means this is C1. This is the literal equality because this graph is equal to C1. And in C1, because now our this subgraph is just a cycle, so all the vertex degrees are equal to 2. That means even. So in this case, the assertion or the implication 1 implies 3 is true, and this is where things start. So then what you do, you suppose that, say, if f is a sum of n number of cycles, then the subgraph that f will generate will have all vertex degrees even. That is your induction hypothesis. Then you consider an element f prime in the cycle space, which is, say, a linear combination of n plus 1 cycles. Now the actual set of edges that these first n cycles give, let that set be f. What you then take is that you take the symmetric difference or the sum of f and the edge set of Cn plus 1 prime. Now by your induction hypothesis, this subgraph has all vertices with even degree, and because of that preservance of evenness of degrees, when we consider this symmetric difference, so because of that, the subgraph that f prime will generate in G will also have its vertices with even degree. So that's how the induction process, it just goes on until we exhaust everything. It's an induction type of procedure, not an actual induction, because our graph is finite, so it will stop at some point. Okay, then the proof goes on. Next it continues like this. The implication, okay, so 1 implies 3. This is how it follows. Next, the implication 3 implies 2. Three implies 2 follows by induction on the cardinality of f if f is non-empty, then this subgraph contains a cycle. Just a moment, okay. Then this subgraph contains a cycle whose edges we delete. To carry out the induction step, or more precisely, this is what whose edges we delete for the induction step. Yeah. Three, it's there, but what was 2? The second statement was this: f is a disjoint union of cycles, or a disjoint union of h sets of cycles. Now, okay, so here also the author is mentioning an induction type of argument on the cardinality of f, that is the number of edges present in f. Say, okay, so here what about the basis for the induction here? If f has nothing, say f is empty, and as such its cardinality is 0, then what happens? Then what about this graph? This graph will also be empty. Okay, now in this case, because we are talking about the implication 3 implies 2, in this case, in the empty graph, what about the status of this statement when the graph is empty? Is it true? Yes, it is true. It is vacuously true, because you see what the statement says is that if you choose a vertex from this graph, then that vertex has even degree. Because here there is no vertex, so this statement is vacuously true. It is true nonetheless. So that means here we can start our induction. But then what is the second one? The second one says that f is a disjoint union of cycles. In that disjoint union, you can consider the empty union. I mean, the union of a collection of cycles in the graph, which is the empty collection. That is also a sub collection of the collection of all cycles. So that way we can consider F to be the empty union, because when you take a union over a collection that is empty, then you get the empty set. So that means in this case it is true. What else the author writes is this. Of course we have written it here. If F is non-empty, then V comma F contains a cycle. Where is this thing coming from? Keep in mind, something is given to us, namely that all the vertices in this graph whose edge set is precisely F have even degrees. Does that mean that there should be at least one cycle in this graph? Yes. Why? Because you see, if there is no cycle, then that means it's a tree. But in a tree, there should be a leaf, a pendant vertex whose degree is 1. But then this condition that all the vertices are of even degree is violated. So that means it cannot be a tree, and that is why it has to have a cycle. And say such a cycle is C. A cycle C, I haven't written it here, but in the text it's there. There is a cycle C. So what you then do, you delete the edges of that cycle. So that leaves you with this graph F minus C, and you understand what F minus C means. F minus C means that from F we have removed those edges that form this cycle C. Now in this graph, this is definitely less than this. So you can apply your induction hypothesis, whatever hypothesis you are assuming. I mean the hypothesis that the claim is true for edge sets whose cardinalities are less than this cardinality. So that means what will happen is that well, am I saying it correctly? Let me see. Oh yes, then F minus C will be a disjoint union of cycles in our original graph. So F minus C is a disjoint union of cycles. Now what about F? Actually, F is F minus C plus C. Is it true? It is true, because you see in F minus C, whatever it is, it just does not have the edges that are there in C. So in F minus C does not have anything common with C, and that one can just simply see from the structure of the sets also. So this union is actually disjoint union. Already F minus C itself is a disjoint union of cycles, but then you take another disjoint union of another cycle, so F becomes a disjoint union of cycles, and this is where the induction step stops. So that means it goes on without any restriction, and the induction it allows us to have the result for any cardinality, any F with any cardinality. And finally 3 implies 1. So 1 implies 3, not 3 implies 1, but 2 implies 1. 1 implies 3, that is the first part of the proof, then 3 implies 2, then 2 implies 1. 2 implies 1 is almost immediate. What does 2 say? 2 says that F is a disjoint union of some cycles in G. In other words, F is a symmetric difference of some number of cycles because there is disjointness involved. So F is a symmetric difference of the edge sets of those cycles, or F is a linear combination of those cycles, and that is why F by definition belongs to the cycle space of G, which is our 1. So 2 also implies 1, and that's how the statements are all mutually equivalent. So this is where the proof starts. In the next graph theory video, we are going to see that if the vertex set of a graph is partitioned into two sets, V1 and V2, then one can consider the set of all edges which have their ends, one end in V1 and the other end in V2, and this helps us ultimately define something called a cut space of a graph, which, like the cycle space, is also a subspace of the edge space of the graph, epsilon of G. So we will see cut space, its properties, results related to it, and then eventually this section will be over. There are a few more results, and we are nearing the end of this preliminary chapter itself. I must admit that the proofs here have been extremely sketchy. That's the way they are given in the text. But when we actually start the next chapter, we will hopefully see more elaborate proofs, or we ourselves will strive to give more elaborate proofs. Let's see what happens. So with that, I end the video tonight, and the next video is, of course, this coming Friday. And we again go back to group theory from Herstein. So that will be all for tonight. So see you next Friday with Herstein's group theory. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.